Jai Hind, welcome to the course Network Analysis Synthesis, and I am going to discuss about the steady state response of a circuit. Today I am going to discuss if the input is your non-sinusoidal periodic, how will you find the steady state response. So title is steady state response of a network to periodic signal which is non-sinusoidal. We can have any type. Suppose this wave shape we have. If your input is like this, suppose this is your Vt. So how will get the, suppose this is T, 2T, suppose having some amplitude. So when the signal input is your periodic but non-sinusoidal, how will get the steady state response. So here we just take the help of the Fourier series. So this is the given periodic voltage. This is your, say this is the DC value or average value of a given voltage source, and it is from n is equal to 1 to infinity. So it has, this is the amplitude and the function of the voltage source. So this voltage is applied to any RLC circuit or RC circuit, and we are required to find the current, steady state current IT. So here we just use the phasor approach. In this we use the phasor approach. So what we will do, we take the each component. So this voltage is written in phasor form. This is your magnitude and this is the phase angle. For DC value, for nth voltage we can write in this, for an e to the minus j phi n. So we can write the voltage, each component of the voltage using the phasor. So suppose this is the impedance of the network having the RLC or RL or RC. It means it is depending upon the frequency of the signal omega. So current phasor is just take the magnitude of the voltage, and this is the phasor of the impedance. So this is the voltage magnitude, this is the phase angle, and this is the impedance. So it can be A0 by Z. This is your I0 and it was J0. So for DC component we can find the current. For nth value of the current we just write nth component of the voltage divided by j omega, we get the this. So this is the current in phasor form. So this is in the phasor form. So we can find the current for each component of the voltage. Each component of the voltage we get the I0, I1, I2, I3. So steady state current will be summation of all these components. So this is the ITs, this is your DC value, this is your fundamental component, this is your second harmonics, and so on. So it is the summation of all the current components. So IT. So this can be written in this form. This is your DC value, this is the for n is equal to 1 to infinity. So this is the steady state current of the network or the system if the input is your non-sinusoidal periodic. So the main idea is we have to use the phasor approach to find the steady state current. Then how will calculate the average power? So, this is your Vt, Vt we can, this is the given voltage, and corresponding to this given voltage we can find the steady state current. So, this is the current, steady state current, this is the voltage, and this is the expression for power. So, instantaneous power is Pt, Vt and It. So, here this is the V0 is DC voltage component, or we can say the average value. Vn is the amplitude of the nth harmonics. This is the phase angle of the voltage, nth harmonic voltage. This is the DC component of the current or average value of the current. This is the amplitude of the nth harmonic current, and this is the phase angle of the nth harmonic current. So, so how will get the instantaneous power? We just take the product of this voltage and current, and to get the average power, what we have to do? We have to integrate this Vt into It over 0 to t and divided by 1 by time t. So, it is the average power. So, simple expression is very simple. Take the voltage Vt and It, product and integrate over 0 to t, and in the last just divide by the t, we get the average power. So, this is the expression for Vt, simple. This is your Vt and this is your It. Take the product of this. So, on simplification we get this. So, on simplification we get expression for average power V0 I0. So, this is your DC value, and this is the nth component or n components starting with the fundamental, and for n is equal to 1, that is the fundamental component, and n is equal to 2, 3 we can have the harmonics, odd and even. So, this is the average power. So, if we simplify this, we get this. So, this is the expression for average power in the case of non-sinusoidal periodic waveform, we get in this format. So, this is the Vn In upon 2 cos phi n and alpha n, difference of the angle of phase angle of the nth harmonic of the voltage and the phase angle of the nth harmonic of the current. We get the this is the average power in case of non-sinusoidal periodic waveform, or we can say the periodic input. It is better to write the input. So, this is the average power. So, how will get the steady state current in series circuits? It may be purely resistive, it may be purely inductive, it may be the purely capacitive, or combination of resistive, inductive and capacitive. So, how will get the steady state currents? So, take one by one. So, just what in the case of the when the input is purely sinusoidal means it is single frequency, constant magnitude wave same. So, resulting current will also be a sinusoidal, but in the case of non-sinusoidal input, the resulting current will contain some harmonic components, because the input itself has some harmonic components. So, the wave shape of the current may altogether be the different from the shape of the applied voltage, whereas in the case of purely sinusoidal, the resulting current will also be sinusoidal, but in the case of non-sinusoidal periodic wave shape, the current waveform will be the different from the voltage waveform. Now, carry out the analysis one by one. So, when the circuit is purely resistive, okay. So, purely resistive, so it is independent of the frequency, it does not depend on the frequency. So, what will the when this voltage is applied? So this is your first component, second, third, n is equal to 1, n is equal to 1, n is equal to 2, n is equal to 3. So this is the voltage components, voltage components. So if you divide by this component with the resistance of the circuit, we will get the current, this component current, n is equal to 1, n is equal to 2. So when the circuit is purely resistive, the resulting current will be, it is V by R. So this is the first component, this is your fundamental, this is your second component, third component, and so on. So therefore the waveform, the current and voltage will be same, and the percentage harmonics in the current wave is the same as that in the voltage waveform if the circuit is purely resistive, because it is R is independent of frequency, R is independent of frequency, it is not changing, R is not changing. So now when the circuit is purely inductive, so same voltage applied to a purely inductive circuit. So what will happen? So this is XL. So XL is j omega L. We take the magnitude. So this XL is depending upon the frequency of the input signal. Okay. So for the fundamental it will be omega L, for the second harmonics, for the third harmonics, and so on. If it is frequency for the different components, for the different frequency component of the voltage waveform, the current will be different because impedance is changing. So we can see here. So this is your fundamental. This is your fundamental. This is the second harmonic, third harmonics. Okay. And because this XL is changing, omega L, twice omega L, 3 omega L, and this is the angle. So suppose we can look here, I is equal to suppose V angle 0 degree, okay, upon this is your j omega L. So omega L n into your 90 degree, okay. So it will, the V upon omega L will be the magnitude of the current, and angle will be 0 minus 90 degree. So that's why that term is coming, okay, minus 90 degree, minus 90 degree, minus 90 degree is the coming. So we can conclude that V and I voltage for the nth harmonic, the percentage harmonic in the current waveform is 1 by n times than in the voltage waveform. So sometimes these inductors are called smoothing reactors because it is reducing the. So I will calculate the RMS value of the voltage and current. So it is simple. This is your fundamental component, second harmonic, third and fourth one, and corresponding this is the fundamental, first, second and third, and we can take the VRMS and VRMS, IRMS. So to if you calculate the power, then this is the active power upon VRMS and IRMS. So we can calculate the power factor in case of the non-periodic non-sinusoidal periodic waveform by using this. So from the above discussion we conclude that when a complex voltage wave is applied to a purely inductive circuit, the current wave has lesser harmonics than the applied voltage, and due to this the current will be smoother than the voltage waveform and in smoothing reactors. So we call inductors are called smoothing reactors. So inductors are called smoothing reactors. Now take the another case when the your circuit is purely capacitive. Okay, same voltage waveform, take the same voltage waveform applied to a purely capacitive circuit. So this X is 1 by j omega c. This is for the fundamental component. For the second harmonic, third harmonic, and for the nth harmonic it will be n omega c for nth harmonic. Okay. So capacitive reactance is also depending upon the frequency. So we have seen that in the case of the purely resistive circuit, R is independent of frequency, but inductors are changing with the frequency, and at the same time capacitor is also changing. So same thing we can get the current. This is your, so I is equal to V upon Xc. So V upon 1 by omega c. So this omega c is coming in the numerator, and this j, so this j is, so it is coming j omega c. So j omega c can be written as omega c angle 90 degree. So we can see that here it is coming the plus 90 degree plus. So in the case of the capacitive circuit, we are getting the plus 90 degree, whereas in the case of the inductive circuit it is the minus 90 degree. So from B and I it is seen that the percentage harmonics in the current wave is more than that in the voltage waveform. So for the nth harmonics, the percentage harmonic in the current wave is n times than the in the voltage waveform, because this component is coming in the numerator, whereas in the case of it was in the denominator. So the it is 1 by nth times the voltage waveform. So just we can, this is the important conclusion from this. So now we can calculate the Vrms and Irms for the circuit having the purely capacitive. So same expression, 1 by root 2 fundamental component, second harmonics, third harmonics, and so on, and we have the Irms. This is first fundamental, second harmonic, third and fourth. So this way we can calculate the Vrms, Irms, and we can find we have the average power. So average power or active power divided by Vrms and Irms. We can calculate the power factor in case of the circuit applied to a non-sinusoidal periodic waveform. Now take the circuit where both all the three components R, L and C all are present. Suppose take a series RLC circuit, okay, and apply to a non-sinusoidal periodic waveform. So this is X, this is R, this is your j omega L, and this is minus j omega 1 by, so we can write, it is better to write the Xc and it is better to write the XL. Okay. So this is the same voltage wave shape is applied to a circuit containing all three components: inductor, capacitors and resistors. So impedance will change. So this is the for the fundamental component. Fundamental component, this is the R is independent of the frequency. This is your XL and this is your XC. Okay. Now Z2, this is the second harmonics. Second harmonics, R independent, inductor is changing and capacitor's impedance is changing. So this is the for nth third harmonics. So for the nth harmonics we can have Zn is equal to R square plus n omega L minus 1 by n omega C square. So this is for the nth harmonic, for nth harmonic. So impedance is changing with the changing in the frequency. So we can again get the current. So this is for the fundamental component, second harmonics, third harmonics, and so on. So this phi 1, this comprises both the inductive and capacitive values. So this is the phase angle. Phi n is tan inverse n omega L minus 1 by n omega c upon r. So this is the phase angle. This way we can calculate. Okay. Now what are the steps and to carry out the steady state response of a circuit when it is applied to a non-sinusoidal periodic waveform. So what we have to do? We have to take the Fourier series. Fourier series of the given excitation function is obtained. The Fourier series is, suppose Vt is, we can write any, either we go for the trigonometrical, exponential or cosine. If you go for the trigonometrical, so we can see that this is the V0 plus n is equal to 1 to omega an cos omega t plus bn sin omega t. So this is the trigonometrical form of Fourier series. So remember, when the input is non-sinusoidal periodic, we apply the Fourier series, because, and Fourier series is also known as the harmonic series, because the harmonic analysis is carried out with the help of the Fourier series. The Fourier series is also known as harmonic series. So what we will do, the first step is to find the Vt by using the Fourier series. Now circuit elements are transformed from the time to frequency domain. Okay. Suppose this is your circuit element. Okay. R, L and C. So R is independent of frequency. Independent of frequency. It doesn't depend upon frequency. So it, throughout the analysis, R remains R. Then L is, so L is XL. XL is J omega L. So it is omega L angle 90 degree. Okay. Then X is 1 by J omega C. So 1 by omega C angle 90 degree. Okay. So what we will do, just circuit elements are transformed from the time domain to frequency domain. R becomes, R is R, independent of frequency, L is minus J omega L and C is 1 by J omega C, or for the nth harmonic it is n harmonics. Now the Fourier series of the DC and AC components are calculated. So this is V0, I0. Okay. We calculate the n is equal to 1 to infinity Vn cos omega t minus phi n. So this is the cosine form of the Fourier series. The Fourier series can be represented in the three forms: trigonometrical form of Fourier series, cosine form of Fourier series, and exponential form of Fourier series. And each format of representation of Fourier series has relative advantages and disadvantages. So then using the superposition, the Fourier series of the response is obtained by summing the individual DC and AC components. So first we take the response due to the fundamental component, then response due to the second harmonics, third harmonic, and so on. And once we get the response of all the components we just just add it to get the steady state response of the current. So, this is the approach to find the steady state of a RLC circuit when input is the non-sinusoidal. So, suppose input is like this, input is like this is your Vt, this is your Vt, this is your Vt. So, it is a periodic but non-sinusoidal. So, what we will do, we just take the Vt is equal to V0 plus summation n is equal to 1 to infinity an cos omega t plus bn sin omega t, and where an is a0 is 1 by t 0 to t Vt into dt. So, this is the average value or DC component of the voltage. So, this we can calculate V0, we can calculate an is 4 by t or 2 by t 0 to t Vt cos n omega t dt, and Bn is Vt sin n omega t. So, this way we can calculate the components an and bn, these are the Fourier coefficients, and this way we can calculate and find the voltage, and we can calculate the impedance depending upon the frequency, and we divide, we get the response current. So, this is the way to find the steady state of response for a periodic non-sinusoidal waveform using the Fourier series. So, this we stop here. In the next class we will carry out some examples how we will get the response when the input is your non-sinusoidal periodic. So, thank you very much. Jai Hind.